Good afternoon, everybody. My name is Mohsen Mahmoudysepehr from the Center for Advanced Photovoltaic Devices at the University of Waterloo. Today I'm going to give a talk about the Nano-plasmonic application for ultra-thin Nanocrystalline silicon solar cell. I'm going to mainly talk about the importance of the ultra-thin or the motivation behind why we are going toward ultra-thin, and then talk about the device that we have built and the concept of application of photovoltaics. Well, first of all, why ultra-thin film? The motivation behind ultra-thin film is that, first of all, by reducing the size of the devices or the thickness of the thin film specifically for silicon solar cells, we are increasing the open circuit voltage at the same time due to the increase of the reducing actually the recombination center and the recombination rate. We could somehow have better performance, but we have a big problem. At the same time, when we are reducing the active side of the device, we are reducing the absorber performance. Actually, the absorption is also reduces. So, we are looking forward to a concept that we could get a optically thick with physically thin devices. That's the motivation behind the application of the different light trapping techniques. For the device structure, we use the normal PIN structure, but we made a little innovation by just using the aluminum doped zinc oxide as a TCO for back and top contact layer. We didn't use the metallic contact. We developed a transparent amorphous silicon and nanocrystalline silicon, let's say semi-transparent one. We developed a very good aluminum doped zinc oxide as a TCO layer with high conductivity and high transparency, and we integrated it in a larger scale devices. That the final achievement that we have was a device characteristic at around efficiency of 4% with around 750 millivolts and the short circuit current of around 11.5 amps. But there are lots of improvement in these devices because the fill factor is the main limitation for us. We are now at the 45% fill factor, but we're looking to improve it. But this performance is promising because we didn't use it in the metallic contact and we didn't use it in ITO, but we just have a ADO at the top and back contact. Anyway, to furthermore enhance the performance, I'm going to discuss about the application of Nano-plasmonic for specifically the ultra-thin films. Generally, for light trapping, the techniques that firstly initiated was the surface texturing, which for thin film is not applicable because we can't create those size of features in thin film. But another technique which was using this substrate, textured substrate was developed, or developing some sort of most-eye anti-reflection coating was developed for thin film, and they have some sort of advantage. The other part is using the anti-reflection coating, which is very well known, for example, like silicon nitride. These are other techniques that we could use, or photonic crystal, which frag reflector, diffraction grating, or even grating the absorber material itself to some sort of incorporating photonic crystal enhancement. These are some part of the research in this field. But one new field of research is Nano-plasmonic, which I'm going to give an explanation and some sort of simulation result for this. Nano-plasmonic mainly cause an enhancement in absorption through three different mechanisms. Sometimes we are using just one of these mechanisms, but sometimes we are using, or we can incorporate all of these mechanisms for enhancement in the, or light traffic in the device. The first one is light scattering and coupling. We could create some sort of particles as a scattering light, and we could be able to initiate some sort of forward scattering in order to enhance the path of light inside of the observer layer in order to increase the absorption rate. One other technique is by coupling the light toward the local surface plasmon resonance, we are going to increase or the concentration of the light locally inside of the observer layer. So when we increase the concentration or density of the light, we could increase the absorption at the same time. The other technique is by coupling the light to some sort of surface plasmon parental mode. We could trap the light at those modes until the final absorption. by some sort of diffraction grating of the metal, we could trap the light at those condition band in order to enhance the absorption. Okay. Now, for my devices, I have used the application of nanoparticles for the enhancement of the absorption. The technique that I used was final differential time domain because of the accuracy of this technique, although it's a very challenging technique and very tricks are involved in getting an acceptable result. I have investigated the effect of nanoparticle array on top, back, and middle also, but the result that I am going to provide here is only dependent on using the nanoparticle at top of the cell, and I have investigated the different parameters to see that what the effect of the parameter and is there any possible enhancement in the approach for thinking devices or not. I have investigated the size of the nanoparticle, the shape of nanoparticle, the thickness of the device, the type of the metal, the type of the dielectric metal, which is another important parameter in getting a good result, or let's say in getting investigating the effect of these arrays. I have investigated these parameters. First of all, I use aluminum and silver as the main metal because they are the most famous one because of the plasmonic frequency. These are two types of metal, candidate metal, which has the best candidacy for solar cell, specific for silicon. I have seen that regarding the array parameter, the distance of the particle and the size of the particle are one of the main concerns to get the best result. I have investigated and see that for both cases we have an optimal condition in respect to the array parameter regarding the distance and the size of the metal. Both of these shows that we could get a high acceptance increase in the efficiency. Enhanced in internal quantum efficiency was increased for about 30% for aluminum and about 32% to 35% for silver. Silver shows a better performance compared to aluminum, but aluminum also has disadvantage as well. To further investigate the performance, one of the good example is we could investigate the absorption and transfer ratio at different wavelengths. Specifically, this is very critical because we want to see that this enhancement is going to obtain at what's the cost of this enhancement. Because we could see that by investigating the absorption ratio, we see that almost below 400, 450, we don't have any enhancement. Actually, we reduce the absorption ratio because of the positive absorption in the metallic structure itself. And we normally, it depends on the plasmic frequency of the metal. Above that frequency, we could normally obtain a performance in different metallic structure. For example, here, the size of the metal silver nanoparticle increase, and we see that, for example, for the optimum size, which is around 200 nanometer, the diameter of the silver nanoparticle, we have seen the best performance. The behavior also investigated for changing the distance between the particle as well, and we see that for both cases we have a optimum parameter. These are the two parameters that we can obtain, and we could observe the absorption interface of the layer at different wavelengths to investigate the mechanism as well. To compare the aluminum with silver, I investigate the absorption inside of the absorbing layer, the absorption inside of the metallic structure, and also the reflected power from the devices. As we see, we could get a combination of the good performance and somehow bad performance. For example, both of the structure shows the performance of the absorption is good for both silver and aluminum, although silver has better performance for a little wider wavelengths. But the problem is that silver at the same time has higher absorption rate for the wavelength, different wavelengths in respect to the aluminum. That's because of the parallel absorption of aluminum and silver is different. The other thing is the reflectivity, that we see that for aluminum reflectivity is a little higher for some specific wavelengths that we may want to investigate the parameters. So these parameters should be considered for the type of the devices that you are going to use for the application that you want to specify for future. The other parameter is the shape of the devices. I have investigated nanoparticle or sphere, semi-sphere, and nanodisk or disk shape. The most important parameter that I would like to highlight is that almost all of them shows increase some sort of enhancement, although the sphere nanoparticle has the best performance in respect to absorption enhancement. But at the same time, I would like to highlight regarding the metallic absorption. As we see, the lowest metallic absorption happening in the semi-sphere material comparing to a sphere or the nanodisk shaped material. So if we are looking for a structure that, for example, for my application, which is some sort of transparency, semi-sphere shows the best application. But at the same time, reflectivity is also another parameter which shows that, for example, semi-sphere has higher reflectivity. These are some tips that show me maybe the application that I want to use this structure on top is not very good for the semi-transparent cell. But for overall enhancement, definitely they are going to create some sort of performance. The other thing is the spacer or the distance between these metallic structure and the absorbing layer. As I have investigated, generally by increasing the distance of these metallic structure from the absorbing layer, the performance decreases. That's mainly depending on the mechanism of the improvement, which is related to the coupling of the incoming light to the different waveguide mode, which is I explain later. And normally we have a limitation on the distance. We could see that normally if we could be close enough to the observer layer, we could get a very good result. The other parameter that I have investigated was the thickness of the observer layer from 50 nanometer to 200 nanometer. And I have seen that by decreasing the thickness, normally I could get a higher performance improvement comparing, for example, a 50 nanometer nanocrystalline silicon shows higher improvement if I use same nanoplasmonic structure on top in respect to 200 nanometer. This is depending on the waveguide mode inside of each layer and the mechanism which is related to the coupling of these waveguide modes, incoming light to these waveguide modes. Generally, if I want to summarize why I should see, actually I have seen this performance. I have seen these three mechanisms in my devices. One of them was the coupling of the incoming light to the waveguide modes. For example, I have seen it for 50 nanometer nanocrystalline at 885 nanometer. The other one was the near field enhancement, and the other parameter was forward scattering. These are combination of mechanisms. The problem is that all of these parameters, all of these mechanisms involved in getting or improving the performance. And if some parameters changes, they play different role. And sometimes, for example, forward scattering is really important for a nanoparticle array. And if we change the position of nanoparticle array from the top to back, from the top side to back, we are losing this forward scattering performance. Although we have the incorporation of, for example, near field enhancement or the coupling mode, but we are not going to see any improvement from the forward scattering. But at the same time, we could see some minor performance improvement as well. So if I want to somehow summary my result, I could say that the development of one of the ultra-thin devices only based on an aluminum doped zinc crystal was one of the achievements that due to the low efficiency, 4% efficiency, we are trying to use the nanoplasmonic structure for the enhancement of these devices. And considering the application that we are looking for, which is semi-transparency, we decided to use aluminum instead of silver for further enhancement because of the low parabolic absorption of aluminum and better reflectivity of aluminum. So we are going to use this structure on the back of our devices. Also, we have understand that ultra-thin is the best choice if you want to incorporate this type of non-plasmonic structure because the performance enhancement for ultra-thin is better realized for this type of material. The other thing is the semi-sphere and sphere. Semi-sphere is so much easier to fabricate because we can some sort of nano-island formation is happening in the particle structure field. But the sphere also shows us the highest improvement. So both can be some sort of future research for our devices that will be followed in our group. Thank you very much for your attention, and if you have any questions.
For your measurement of the absorption enhancement, how did you separate parasitic absorption and scattering? How did you?
That is the advantage of this software that we are using, because how I am going to calculate the absorption is for the final differential time domain, you can calculate the power at each position of your structure. So imagine you are going to define the structure like this, the incoming light from top to down. When you have the incoming light here, that's the ongoing light. The difference is the absorbed power inside of the absorption. That's a simulation. But for reality, it's very difficult, because once you should, for example, you should synthesize just ASIO silver nanoparticles embedded in ASIO, measure the absorption there, and then you can adjust those absorption to the absorption of, for example, metallic structure. But it's not very accurate, because final devices is different. But simulation gives you an idea what you will see later on in real devices, because I have seen it. For example, in my simulation, right now we are in the middle of experiment making these devices, and we see some exactly real answer based on simulation. Because, by the way, another point is that for the simulation, I use the exact material properties that I have developed in the lab. For example, when I have developed this nanocrystalline silicon, I measured the transparency, I measured the N and K, and the measured N and K was the input of my software. I didn't use any literature or any info in the literature books for the nanocrystalline, because it's developed in the lab. I did the same for ASIO. The only thing that I used from the literature was the glass substrate, because it was not very important for me to device.
Yeah, one quick question. Okay. Yeah, so you mentioned that increasing the light concentration can increase the absorption coefficient. So what's the mechanism by which that occurs?
Okay. Actually, I wasn't sure if I can show you this movie. That's why. Oh yeah, I have it. This is the whole phenomena which happening from incoming light. As you see, the incoming light causes the resonance effect inside of the metallic particle. That's the plasmonic resonance. And and as you see, exactly this resonance cause a light increase exactly at the interaction of these metallic with the absorber layer. You see this enhancement due to the resonance enhancement. Actually, incoming light cause the free electron resonance with the resonance of the incoming light, but that's a very theoretical condition, because it depends on the size of this particle, how these free electron inside of metallic material is going to resonance in incoming light. This resonance is going to be re-radiated in the forward direction, and as you see right now, it's still visible here. This resonance causes the concentration of the light only increase locally, which depends on the position of that metallic particle in respect to the absorber light.
Right. So I was wondering, how does that actually result in increased absorption?
So when the intensity of light, imagine, for example, you have a 100 watt of light. For example, you have now 1200. So the intensity increase. It looks like, for example, very simply, instead of using 1.5 AM light, you're using AM1, because the intensity, the number of photons increase because of the resonance effect. But this is locally happening, for example, at a specific wavelength. For example, as you see, for example, this shows the increased efficiency due to the intensity of light absorption increase and the forward scattering. All of these phenomena happening at the same time. But the most important is forward scattering and the light concentration increase.
Okay, thank you. We have to move on. Thank you very much.